The first talk will be given by Dr. Hsiao-Wuen Hon, who is the Managing Director of Microsoft Research Asia, located in Beijing, China. Dr. Hon received his BS degree in Electrical Engineering from National Taiwan University and PhD in Computer Science from Carnegie Mellon. From there, he started his career by working for Apple, where he led the development and research for Apple's Chinese dictation kit. And then he joined Microsoft Research in Redmond, where he worked on speech technology. And from there, he transitioned to a product group, to the speech technology product group in Microsoft, where he worked on the Microsoft Speech Server product. And after doing that, he went back to China and joined Microsoft Research Asia, for which he's the managing director right now. He's well known for his research in speech technology. He's on the editorial board of CACM and widely recognized both in the academic community and inside Microsoft. Please welcome Dr. Hon.
All right, thanks, Yuron. And it's my honor to present to you using the next 30 minutes to show the exciting thing we are doing in Beijing. So I just really recap of what Rick said. We have 6 labs, and we are the one based in Beijing. I want to extend the invitation to all of you when you are in the Asia Far East, we call Far East or Asia Pacific, please visit our lab, and I think that we can show you more stuff and then explore the collaboration opportunity. And we found almost actually a little bit more than 11 years ago, and just like the MSR India and other MSR lab, we actually do fundamental research, we do academic, we publish a lot of papers, we also do tech transfer, and we also participate in Microsoft IP licensing program. And right now we have more than 200 full-time researchers and engineers. So we do research in pretty much most computer science area, which you can imagine. And this is just some of the representative papers we publish in those conferences. And I roughly actually divided all the lab research activity into 5 different areas. And the first one is natural user interface. And in the rest of my talk, I'm going to actually pick a couple to actually show you the work we currently being conducted in the lab in Beijing. And second one is the data-intensive computing. As you know, all the data mining stuff and the web-rich data, whether it's for consumer-facing or enterprise, and how you build the infrastructure to take advantage of those data and generate from the raw data, generate the information and knowledge, and eventually become some business intelligence. And so, Microsoft, company like Microsoft or even other discipline, other discipline can take advantage of. And the multimedia, as a lab, we actually do a lot of multimedia stuff. Again, in the rest of my talk, you will see some of the multimedia work we actually doing today. And search and online ads, which is a very hard topic, and I think that's also another focus area. And the last but not least, I call computer science fundamental, which is including all the system networking theory, which basically, when you're actually building any application or any computer system, you actually need those kind of fundamental technology. And again, those stuff typically kind of difficult to show, but I will try my best to show you 1 or 2 of such examples. And based on these 5 areas, and these are the research group we have. And again, the best way to know more about us and explore the future collaboration is visiting us. And I will do the same by sending more researchers to India and to your institute. And I think the research is all about communication and collaboration. And hopefully we will have some chance to work together in the future. Microsoft kind of view for the industry in the next couple, whatever years, is what we so-called 3-screen plus a cloud. Of course, we know the emerging of the cloud computing and data-intensive, data-driven computing, plus the richness of the client. And the client actually, they are actually more important, not less important, because eventually all the rich knowledge in the cloud need a terminal, need a client device to reach people. And I think the TV screen represent all the entertainment experience, and PC continue to be the productive machine environment we do in our office or when we travel. And then the mobile device represents something you carry all the time, whether it's for the work or for the other personal usage. And I think I don't need to actually say more. These are really the work is going to drive the industry in the next whatever years. And I think the one thing I think we recognize in Microsoft research is because all this excitement and also opportunity, the interdisciplinary and multidisciplinary research become even more important. And I think the interdisciplinary means all the interdisciplinary within computer science or across to the different area. And I think in this morning you heard so many exciting stuff I don't need to repeat. And I think here I just want to emphasize how important for anyone to really look out of their own immediate research expertise in the industry, and then by talking and working with more scientists and engineers in different disciplines. And the lots of innovation actually happen this way. And then in the future, I think I will argue it's become a requirement for any research area to actually do something innovative. And the first demo I'm going to show, which is also my own area, is on the speech, which is the speech generation, speech synthesis. And actually, as you know, lately, one of the most talk about thing is the movie Avatar. And I think we are trying to build a realistic avatar for very different applications. And this is really one of very important component for the natural user interface. The speech interface, of course, what you speak is being recognized by computer, which is speech recognition. And the speech synthesis plus a realistic avatar is really for computer to actually communicate with you, and then but has the human touch. And I think all the cognitive study actually show, and this is actually very, very important, particularly in this social computing world. And I think it will actually provide a new opportunity for a new slew of application. And typically, I think in the synthesis world, we have two different approaches. One approach is the third row in the bottom, which is taking the waveform, is a cognitive synthesizer, whether it's in speech synthesis from or in the vision synthesis from. And but this approach, the advantage is you take in the real speech sample. So the sample itself sounds as natural as you can be because it's a recording. However, the juncture will actually present unsmoothness and glitch, which could be very annoying to our ear. This is why the other approach is the top one. It's a model-based. In the 60s and 70s, like a my talk and deck talk, which is using the Foreman synthesizer, which is using some acoustic model, which it generates a very smooth voice, but sounds like robotic. And I think lately we use the hidden Markov model to actually model more sophisticated acoustic trajectory. And I think that's HMM-based TTS. And the work has been done in the Beijing lab. We're trying to really combine the beauty of the both approach. We call the HMM-guided approach. The basic idea is once you have the model trajectory, which is kind of artificial because not a real sample, we use the trajectory to actually select the acoustic unit, the speech unit, which will match the acoustic trajectory the best. And I think by doing so, we can kind of get the best of both worlds. And then doing the avatar, we kind of extend this approach to our audio visual data. So now you have a speech input. You're using this to actually find the trajectory in your, again, HMM-based visual. In this sense, in this context, is the lip movement. And then, of course, you also have all this lip movement real visual example in your database, which is the bottom row. And we're using this HMM visual trajectory to guide the selection of those two real lip segments. So this is kind of another diagram to show you. So you have on the top, you have the trajectory produced by your model. It's a hidden Markov model. And the bottom is like all the candidates which will be classified into each HMM state. And based on the model, and you're trying to pick the sample sequence, also give you the most smooth transition. And this is basically how we do it. Now I'm going to show you the effect. So So on each sample, we have two samples here. On each sample, left-hand side is the original one. The middle one is the HMM pure model-based one. And the right one is HMM guided one. All right, with some glitch, but we fix it. So now here is the sample. And you can hear the second example.
On May evenings, the rooks were busy building nests in the birch tree.
So I think you can trust me. Really, the HMM guide is very good because I will show you the other evidence why. And here is the diagram show you how we actually do it. And I think the most of what we do is the lip part. And however, if you can see if the other part of the face not moving, it will sound robotic. We have other projects working on the visual cue, which is your so the face expression and eyes. But on this pure speech kind of driven talking head, we just do a simple trick by actually taking some random movement of the eyes and give you more realistic view of the whole avatar. And so the result here is one for we actually input the real speech.
The grammatical agriculturalists woke the beneficial corduroy.
And the next one you're going to see is we actually have the text input. So the difference is the previous one is the real human's voice. We use the voice to find the corresponding lip part and by actually play the talking head. And this one, is the input is just text. So we use the text to generate a speech first and use that speech to drive the talking head. And you can see the
I'm Samantha, a new storyteller born in Microsoft Research Asia. I'd like to tell a story, The Little Girl and the Wolf, by James Thurber. One afternoon, a big wolf waited.
Okay, I will stop there and then, okay, I will show you this one. Yes, we actually just in the latest, here. The latest, the LIPS Challenge 2009, and we just got the #1, which is, they actually, of course, they have the real human to actually look at the talking head and listen to the sound, and by using the human judgment, and I think our system actually been rated #1 in the test. So I think obviously we actually must be done something right. And here is the other one. We actually haven't put the real talking head. We actually think a nice application, particularly in Asia Pacific. I don't know, well, I think in India, I don't know really how karaoke is popular or not. And I think the people in the speech community will know singing is actually easier than speaking when you actually train the computer singing. The reason is people actually might say, well, how can this happen? Because when you sing, you actually sing according to the tune. And the tune actually, if you represent by the MIDI file, which specify the tone, how high, how low the tone should be, and also they tell you the duration for each syllable, how long it should be. So this is why typically even people like me who has accent speak English, but if I trying to sing the English song, by follow the right tune, actually my accent will be gone. So the accent is actually captured by the MIDI file in this sense, the tune. And then when you speak, that tune is part of our accent. And that is really very subtle because you cannot possibly actually write the MIDI file to specify how each sentence should be spoken. So in any event, let me play the singing completely driven by computer, the text-to-speech.
Edelweiss, every morning you greet me, small and white, clean and...
Okay, I'll stop here. I think you can judge by the quality of the singing. And I also can guarantee, currently our technology can recall 30 minutes of your voice. Then we can generate a text-to-speech system, can speak any sentence, and sometimes actually can even speak any other language, as long as your recording cover all the basic sound, which is the phoneme in the other language. And then I can guarantee the TTS system we build can sing better than you because you will never be out of tune, once you're a MIDI-file, no matter how high, you always can sing up to that high. No matter how low, you can sing to that low. And you can even sing as long as you could without taking a breath. And I think so I think if you want to enter some karaoke contest, just bring your talking head, then you will definitely be the champion. So, and the next one I'm going to show you is in Beijing we call e-heritage, basically the same as the digital heritage here. And I'm sure people can easily understand the value of this. We have so many cultural heritage, and not particular for a lot of people, whatever billion people, which not necessarily can enjoy those cultural heritage. Using the modern IT technology, we can actually preserve it, we can digitize it, we can actually put a nice multimedia or sometimes even real-time interpretation, disseminate it. And I think we actually work very closely among the MSR lab, also including the colleague here. And there are so many cultural heritage components around the world, and we're trying to see how we actually can use technology by also working with a domain expert in academics and also in those museum or those cultural heritage sites. And here is we actually make a quick video.
Each nation's heritage represents its past glory, its present identity, and its future inspiration. In July 2008, Microsoft Research Asia launched the unique eHeritage program that applies the latest computing technology to digital preservation, virtual restoration, and the interactive display of unique historical treasures. The eHeritage Initiative preserves cultural heritages through the application of advanced computing research. Let's explore some of our key technologies. The original beauty of ancient objects may be obscured by 1,000 years or more of weathering. With the Microsoft Appearance Manifolds technology, objects can be viewed at each stage of the weathering process in a virtual world. Priceless jade objects are often sealed in museum display windows. Microsoft proposed the first GPU-accelerated diffusion equation technology, enabling screen presentation of lifelike translucent images of jade and light, supporting touch-based interaction and full-angle viewing. Museums use high-resolution digital cameras for archiving their ancient paintings. The gigapixel digital camera invented by Microsoft can create digital images of over 1.6 gigapixels at a reasonable cost. These photographs are more than 6 times sharper than the images the human eye generates. The concentric mosaic has been applied to the virtual terracotta warriors that provides the richest possible 3D experience without requiring a scene's geometric information. In addition to inventing key research and enabling technologies, Microsoft is also partnering with academia on heritage preservation. The Bayon Temple in Cambodia presents an enormous challenge to create a digital model at a 1 centimeter resolution. We provided the Windows-based cluster, which dramatically reduced the processing time for this huge amount of image data. Animating Chinese paintings immerses users in the beauty of Chinese traditional culture via play. Now we are collaborating with universities and museums to annotate one of the greatest Chinese traditional paintings, and to virtually represent the 3,000-year-old Mao Gongding. Microsoft Research looks forward to working with...
One example how fulfilling actually when we work on this project. I mean, of course, the digital representation that more people enjoy it. The other thing also, it's really can preserve in a way we never be able to. For instance, we actually went to the Dunhuang, which is the one of the very important destination in the Silk Road. There's a lot of cave painting. Over the century, over the year, the painting actually changed color. And then now, not only we can preserve, we can also preserve in a different time. And I think so 30 years, 50 years from now, people not only can see the cave painting, then they can also check 50 years ago, 40 years ago, 30 years ago, how the color got changed. And this is something which really is more than just really doing the digitalization of the current form. It's really something we can preserve in a way which the human being never be able to actually not just enjoy, also doing research about. And also through this project, we also doing some research, not only for this project, which actually can have other impact. Well, for instance, we actually built in one we call gigapixel camera. So this is the real camera, which is I think the probably like this big, and which is in our lab. And then we actually build this camera totally on our own with some reasonable, like the 10,000 also the dollars. And then we do a scanning, and we get this gigapixel, 1.6 gigapixel for each shot. And I think when the team actually built out this camera, I say you need to shoot some picture. The first picture they shoot is a dollar bill, and I don't know why, but they're trying to, maybe they just want to find out are there hidden messages in those US dollar bill. And then, but seriously, I asked them to just go into a museum to take more picture, because I think we can really, for some of those really historical painting, we like to actually study in the fine grain, which we cannot do before. And this is just the sample of the picture. Here's a comparison. We compare this with like the very, very high-end photo scan machine currently available, and you can clearly see the difference, how this gigapixel camera can capture the detail we never be able to do before. And here's another example. And here is we actually combine this camera with our other technology to actually get the depth information, so we can reconstruct some 3D model. So here is, let me show you this short video. So with gigapixel, we can see all this detail and combine with the depth information. So we like, particularly for all-year painting, we actually can get all the paint, the thickness information in a 3D form. So I think that we can use this to study the things we cannot do before, and also this will be good education and the research value for those prestigious cultural heritage. So next demo I'm going to show you is like some of the image technology in the multimedia area we are doing in the lab. So first one, everyone all have this experience. When we take a picture, our hand will move, so you will get a blur image. And this is, in the math, is basically a convolution process. And to actually get back to the original clear picture is a deconvolution problem. I'm sure everyone this morning raised your hand, you say you love the math. Of course, you will know this math principle. But the key is, this still, you don't have a closed form solution. So we actually develop a technology, has an iterative the algorithm which we can combine with the kernel function, we can get back to the clear picture with only single shot. I mean, so in all this example, we only take one single shot with a blur image, and we can actually recover something like this. And here's more example, a picture of a painting, and going through our progressive deconvolution algorithm, we can recover. And here's another one. And we compare our approach versus some of the technology in this area done by other research institutes. Here's another example. Okay, so hopefully this will be incorporated in some of the photo image processing tool we all can enjoy. The next one is, I mean, Beijing or China, right now it's getting better. Like all the pollution and all this stuff. I know India probably also have this. And then it would be nice when you take a picture and you get all this hazy stuff. Oh, India now, I heard like the Delhi in the winter time has a lot of fog. Like sometimes either it's foggy weather or the pollution. And it will be good. We can actually recover a picture like in the center, right? And when all you can do is the haze can take is only a haze image. And then if you analyze the math on this, the foggy image, there's a fog, and based on the distance, well, I think something kind of changing. Okay, go back. Right. So if you know the depth information, then you could easily recover the original picture like in the middle, because the point which is further from the camera, your attenuation of the light will actually become lower, and the one closer you actually can see a little bit more. So all you need to do is you need to somehow need to know the depth. As you know, you take a single photo shot, you cannot possibly get depth. So our researcher is like to see how we actually can get this depth information. So we look at the dark channel. For people not in this area, thinking about dark channel is picking some kind of pixel, some kind of, well, for instance, this instance, 15 by 15 pixel. You pick the darkest point, using that point to represent the whole pixel. And what we find for the haze-free picture, the dark channel is actually very dark. Look at this. That's the dark channel for these two pictures. It's very, very dark, almost invisible for human's eye. Here's another two examples. There are more. And why? So we kind of figure out why. The 15 by 15 pixel, if you have any shadow, so thinking about this, the dark channel is getting the minimum value of RGB value from that pixel. So anything you have one dark, you will make it completely dark. And second one, for the colorful stuff, RGB, you take a minimum of R or G or B. So this is why it actually will become, not to mention some of them actually are already very dark. And however, if you have a hazy image, because the fog or the pollution, the dark channel come out of that, it's not very dark. So that's a very interesting the observation. If you look at the dark channel of this haze image, well, so you will notice the dark channel it actually gives you some depth information, because it's not very dark. And you look at this, you can see it actually gives you a depth information. Based on the depth information, we can apply our algorithm to actually take an original picture like this, recover it like this. So now we can have the smoke-free, fog-free Delhi or Beijing or Shanghai. Any picture you take, you can actually recover quite nicely. Okay. All right. We are all researchers, so people will challenge me. That's good, but do you screw up the other picture quality when you do that? So we kind of doing a stress test. If I take a very clear picture, haze-free picture, apply the same algorithm, what can we get out of this? So here is one example. And you can see we didn't screw up that much. Actually you will argue for most the practical purpose, it's actually done pretty good. So this means we actually have a chance to apply this algorithm on any picture you take, whether it's haze or not. And I think that certainly makes the application of this technology very, very meaningful. And we also apply this technology to video. So now you can see the contrast demonstration. It would be nice the real world can be like this. All right. Okay. Next two demo I'm going to show you is the search related, also data intensive computing related. The first one we call entity cube. A lot of people on the internet search for name, search for people, and we use the technology automatically mine all the information about any name entity, and trying to put all this information together. And I will probably let you actually try yourself, because this is something we already put in the public. You can type any name, and for now I just pick some obvious, like Obama. And then I think that I just quick. And then it will show you, so the people has a relationship with Obama. All the information is automatic mined from the internet. And I think also like article about that person, and even the bio or quote, we actually just directly doing data mining, extract from the internet. And I think you will be very surprised how much information about you or about any person on the internet. So on the internet, really, there's no secret. But I will let you try yourself, because this is something in the public, and you should try even for yourself or the name you are interested in. The URL is entitycube.research.microsoft.com. So this can save us time for the time we lost because the AV setup. So go to next. Oh. The next one is our version of academic search. We work with the Binting, which this is just a current prototype. And then again, the URL is academic.research.microsoft.com. We just like the paper search, but we actually extend this to actually treat each paper, each person an object. So their relationship about each other, the co-authorship, and also from there the conference and the journal. So because of time, I would just leave the URL to you, and you will try yourself. Of course, and also how the paper got cited, the citation information. And I think again, I'm sure you will find, particularly for research like this, you will be interesting for you to find out how you and your colleague or your paper actually fare in those kind of search, and you will try yourself. And the last one I'm going to, that's why it's a system. Actually, it's a networking project. So it's all just PowerPoint presentation. We actually did something in the lab called software radio, and the basic idea is trying to reduce the hardware part as much as we could. Of course, you still need a radio. You need the A to D, D to A component. But the rest of the stuff, we want to do it all in software. And I think the reason, the value is quite obvious. Because when we do wireless the research, a lot of time we kind of waiting for the standard, waiting for the hardware component, the protocol, whatever, for us to actually go to the next step. And with the software, you can try all kinds of the idea before settle on. Eventually, you probably, most likely, you will still need to build the ASIC and hardware. But this will speed up the whole ecosystem. And then to have a more wireless, particularly all this wideband stuff, which allow you to do all this experiment. And I think whether academically or for the industry. So we already generated a lot of interest from the academic and the industry. And I think now for the multi-core PC, this is a very good way of using the excessive the computing power for us to do this software only the wireless platform. And we actually, MSR, the external research, we actually make this available and to our academic and industry partner to actually use this platform to do research. And we also very glad we got recognized in the NSDI, the base paper and demo award, and also recognized in some other conference. But most exciting thing, I think, if you are interested, I think we have the program in our external research department, which would like to work with you. And I think because we believe platform like this, we actually open a lot of door for the future wireless research. So I will just give the next demo and just stop here. I mean, we actually have more other stuff I can show you, the hardware related, system related, and like I say, I will extend the invitation to all of you when you are visit China or in Asia Pacific, and you can visit our lab. I can show you more stuff, and I think hopefully some collaboration can happen in the future. So I will just finish my talk here, and sorry for the AV, the hiccup during my talk. Thanks.